So, good to see that many people back. I guess you liked the last lecture, which is nice. So today is going to be introduction to networks, networks. We're not on LinkedIn, but you get the idea. So to start the thing, I wanted to give a small quote from Stephen Hawking, which is, "We're all now connected by the internet like neurons in a giant brain." This guy, he has a huge brain, so which makes a bit of sense. So, like last time, let's start by a small definition, because why are we going to look at networks if we don't know what are networks? So a network is, you can consider something being a network as soon as there's two devices connected to each other. So it's just a warning, today is going to be a big overview. If you guys have some stuff or any questions or things that you don't quite understand, stop me right away, because there's going to be a lot of content. So hopefully everyone's up for it. So a network, stuff that can qualify as network is within a network you can share data. So you can share file, email, messages. You can share resources as well. So a printer is considered as a resources. Storage, like a server where we have a storage, is also considered as a resource. And then the internet as well. So, and also enables communication, because this is probably the major part in a network. It enables us to communicate devices to devices. So I like IBM because they do good definitions, and the definition for a network that I put is a computer network is a system of interconnected computing devices, which qualifies to, as you know, got computer talk to each other, that's a network. And then ranging from traditional cloud-based environment, let's not forget the cloud, that communicates and shares resources with one another. All good? Okay, perfect. So why do we need networks? Because, okay, we know what are networks, but why do we need them? Communication. Makes sense. You know, you need to be able to chat with your mates. Sending a postcard is good, but nowadays you need more than a postcard. So emails, chat, video calls, resource sharing, as we said before, printer storage applications, data access. Without network, you cannot access the university database. You cannot access LA. You cannot access anything. So you need the data access. Cloud services, like you got OneDrive, everything. And then websites, quite useful. Collaboration, yeah, you can work on Google Docs, Google Sheets, Excel documents in collaboration. And without networks, you wouldn't be able to do that. So that's quite nice. Scalability, which is a good thing about networks, because once you can have two users, if your network is configured correctly, you can have thousands. If it's configured correctly, then that's most often not the case. And cost efficiency, when you share stuff, costs less than when you have one thing for individual persons, which makes a bit of sense. So network and cyber, why are we going to look at networks and why is it really relevant for us as cybersecurity enthusiasts? So they matter because most of the cyber attacks go through networks. If you want to send phishing emails, you need a network. If you want to do denial of service, you need a network. If you want to do a man-in-the-middle attack, you need a network, and you get the idea. So yes, cyber attacks are often targets or travel through networks. So as the attack stated before, don't worry too much about this graph. It's just to give a small idea about stuff that can happen with a network. It's just a big overview. And we come back to the thing we love, the CIA triad. So if you were here last week, we talked a bit about the CIA triad. And in this case, it applies perfectly. So networks, you need certain confidentiality, so you need to encrypt your data in transit with VPNs or with TLS, which is a security protocol. So this is confidentiality within a network. Integrity, you need to detect a certain tampering, so you get hashes, you get checksums, all these kind of checks to see if data hasn't been tampered with. Then you get availability, which protects against certain disruptions like and you got DDoS protections, which is distributed denial of service. So it's just when you send a lot of traffic to a host and say if it's not made correctly, it's going to go down. So this is a denial of service. Then you get IDS, intrusion detection systems, just detect when something goes through a network, firewalls, and all those things. So the list is non-exhaustive on the things that protect availability on the network. Then you get network devices. So I got a switch right here that I'm gonna give you guys. You can pass it around. So this is what a switch looks like. It doesn't do a lot of stuff, just a few Ethernet ports. You plug something here. So this is a plug-and-play switch, which is not a managed switch. So you won't be able to set up specific VLANs to specific networks, so virtual local environments. So the first device we have here is a router. probably all heard about router. If you guys want Wi-Fi at home, you need a router. So this connects, this makes your home Wi-Fi and everything that you mostly need. So router connects different networks and direct traffic. It's also your gateway to the internet. So it's good to be able to connect all your home devices together, but if that's the only thing you can do, it's not very useful. So it also enables you to connect it. Oh, thought my switch was dead, man, I was scared. So this is the switch, no, not this one, this one. So this one is not exactly the same one as I'm passing around, but it's mostly serves when you don't have enough Ethernet ports, or when you don't have enough stuff to get connected, you use a switch, which gives you much more access. So you can plug a switch to a switch to a switch, and you get the idea. Of course, the traffic and the speed is going to be affected if you do that, but it works. Then you got firewalls. Most of the home networks don't have firewalls, or maybe your router has a firewall, but it's not going to be very powerful. You got physical firewalls and you got software firewalls. Physical firewalls like this one. Fortinet is a big brand that does that, so it's quite useful. Big stuff, costs a lot of money, so if you're not in industrial, you wouldn't really need it. And you got software firewalls, which cost less money. Most of the time they're subscription based, so at them in the long term you might pay a bit more money. But it's good for controlling and filtering traffic security. So if you put on specific rules for your traffic, this is perfect. And you got servers. So this is a server room. So it provides services. So but not only, you can use it as a computer, a big powerful computer, or you can also use it to host web servers, email servers, file storage. You get the idea. So now we go through network topologies. So what are network topologies? So your home network might be a bit, randomly. You just connect your computer, connect your other computer, you got a printer in the middle, that's it. But for enterprise systems and enterprise architectures, you need a real topology. You need something that's structurally valid, because if you just connect random stuff, you might fail on the device and might kill your whole network. And that's really what we want to avoid when we have big enterprises, and when a second of downtime might cost $1 million. So we don't want that. So the first one is the bus topology, which you can see here. I need a laser pointer. I'm going to invest in that. So the first one is the bus topology, where you can see there's a single cable passing in the middle connecting all the devices. It's nice, but as you might have guessed, there's a bit of an issue on that. It's very cheap, so you don't need a lot of cost. But the big issue is that if there's a failure at the start of the bus, you can guess that all the devices after are gonna be unavailable. So it's good if you don't have a lot of budget, but enterprisely it's not used. Start topology, which is the one right here, has a main device in the middle, and all the devices are connected to that. So most of the time a switch is in the middle to transfer the traffic, and one of the devices is a router, and you get the idea. So this is also nice, but there's a single point of failure, which is the switch in the middle, which is also, so it's still cost effective, but it's also a bit dangerous when you're using it in a company. Ring topology, everything's connected, so in a big circle. It's nice, same thing, if your one fails, so if imagine, do I have my mouse here? Yeah, I have my mouse. So if imagine there's a failure on this device, all these devices can still communicate together, but this device is going to be a lockdown. And if it's only a single way of traffic, if there's a cut here, then you're dead. So this one can still communicate to this one, but all the rest will not be able to go back here. So ring topology as well, it's a bit of a mistake. Mesh topology is the one where you really don't want any failure happening, so you just connect everything together, which is quite nice, is very, very secure, but as you could probably guess, not very cost effective, because you need a lot of cables to do that. And you got hybrid topologies, so some companies do like to set up different topologies, so I think there's an example here. So there's, maybe in my notes, so some enterprises like to set up mesh topology within a building and then connecting other buildings with a different topology. So it depends what environment you're in. Give me a second. So as well, why it matters. So reliability, of course, like we said, if you got a failure and your topology is a single point of failure system, it's going to be complicated to explain to your boss why you don't have Wi-Fi for a few days. So of course, reliability, of course, is a big factor in that. Performance is as well a big factor. You can guess that if you have a bus topology, if there's a lot of traffic coming from computer 1 and 2, then computer 3 and computer 4 are going to have a bit more of a hard time communicating together. So if you have a lot of cables, like in the mesh topology, it's no problem. Data is distributed correctly. There is no stress on the network. It's nice. Ring topology is also a bit of an issue. Tree topology as well. I mean, you get the idea here as well. And security, which is the biggest factor for us. So when you got a centralized topology, like the store topology, nice. But what happens if you get your central machine hacked? It has access to a whole network. So definitely need to take a look at the security aspect of the topologies. Is when you have a central topology as well, it's easier to monitor your devices. Again, we're speaking as a company, but it's risky. If you get compromised, the whole system is down. And the mesh topology, we said a lot of positive stuff about the mesh topology, so it looks like, wow, the perfect system as long as you have money. But how are you going to monitor that, man? How are you going to monitor something that everything is connected to each other? So definitely, that's a bit harder. It's like the CIA triad, like we said last week. It's balance. What you want to do, what your organization is doing, how you want to handle things. If you want really, really secure system, you might have some hybrid topology, like we said before, or it really depends on what you want. So we're going to go quickly about the web and the internet, because this is going to be next week's subject. But you need to understand some stuff, is that the internet and the web, not the same thing. We often use this term interchangeably, but it's not the same thing. So the internet is an interconnected network, so big network of computers. And in practice, interconnected networks of computers that span the globe. So the internet is everywhere. So you might have some guy that has Wi-Fi in the Antarctica. He's connected to the internet. Perfect. The web, in this case, is not the internet. The web is the collection of web pages made available by a web server. So everything you see with HTTP or HTTPS is the web. The rest, the internet. So the internet is used to deliver the content you view on the web. The web is on the internet, but the internet contains much more than the web. A web is a subset of the internet. Just quick definition. We're not going to go a bit more in depth in that because that's going to be next week. So you might have heard the term LAN. You might have heard the term WLAN. No, yes, no, yes. Okay, perfect. So LAN is a local area network, connects your device together in one physical location. Your home is a LAN, the school is a LAN, the campus, even if there's a lot of machines connected, it's still a LAN because it's a single physical location. All good? Okay, perfect. So example, home, school, office, campus, yeah. Scales from a single user at home to thousands of users in a company. A company is still a LAN as long as it's not spanned around the globe, it's still a LAN. And the purpose is to share resources, as you could probably guess, printer, storage, internet, and to enable communication with those devices. So you'd like your phone to be able to airdrop to your computer at home or anything regarding this matter. Or in the university, you like when you send something to your printer, you like to be able to access it at a library, thanks to the LAN. Ooh. So what is a WAN? Now, so the WAN is a wide area network, as you probably guess. L is local, or W is wide, sorry. So it connects devices across large geographic areas. So it's the opposite of a LAN. Example, the internet, corporate networks connecting offices worldwide. So as said before, if you have a company that has a multiple office everywhere in the world, you would probably have a WAN. If you have a big company but has a single office in London, you'll have a LAN because they don't need to have a wide area network. So scales cover cities, countries, or continents, big scale, and it enables communication and resource sharings across long distances. That's very recurrent. One wide area network, you want long distances. Okay. Now, the OSI model. Ooh, this one is a bit complicated, but not too much as well. So the OSI stands for Open System Intercommunication. It's a model. There's also other models that are used to represent how everything works. How we're gonna focus today on the layer 3 and the layer 4. So the layer 3 is networks. Yes, go for it.
It's the same thing as TCP/IP.
So this is one other model. It's in the same family of models. So you might use the OSI model, you might use TCP/IP model. It's the same stuff, but not really the same stuff, but it's in the same family. So really depends what your preference is. This is a very used model academically, so that's why I would like to go through it. But the TCP/IP model is also a model that is used a lot. So, but here in the OSI model, you mostly talk about the layer 3, the layer 4, and that's mostly it, because all the rest is handled. So let's go through it. So the application layer would be top layer. So really top layer, how you access the web page, HTTP protocol, HTTPS protocols, all that thing, SMTP, which is a simple mail transfer protocol, Telnet, all the SSH, a lot of protocols. Then you get a presentation layer, which is, have you ever coded a web page, code in HTML, GS, all that things. You have files like JPEGs, you have MP3, which are via sounds and things like that. So this is within the presentation layer, used to recognize data. Then you got a session layer. This one is a bit hard to understand. So you got TCP, it's like sockets in a computer. So you have ports in a computer that are used to access specific service. You got 66,000 ports, a lot of something like that. And you got a lot of ports, so you need to associate specific ports with specific service. So the session layer is the one handling that. So making a session is a client connects to a server, and that's it. That's a big connection. So this is the server, the session server, the session layer, sorry. Then you got transport layer, which is the one we're going to see. So you got two big protocols that we're also going to talk about, TCP and UDP. Though these are the big internet communication protocols. Then you got SSL, TLS with our secure protocols. We're not going to go too much on depth on that. Then you got the hardware layers, network, data link, and physical. Physical is really the cables. So, this layer is really the stuff. So your Ethernet cable, your switch, for example, I don't know where it is, but it's right there. Then you got your VGA, you get the idea. It's really the cables. Then you got the data link, which are the protocols these cables use. And you got the network, which is where we are, which is how does data addressing. So when you send a post letter at the mail, this is when you need to find the address. Same thing. Think about the network layer as finding the address to something. So you got the ARP, IP protocol, and we're gonna go fast through the rest. So yeah, I think we said most of it. So let's talk about the network layer more in depth. What's the protocol? Move data between devices across different networks. So function, logical addressing, like we said before. How do you know Google is there? Just type Google and that's it, magic. But no, so it's something, it resolves the name Google to an IP address. So this is really your address. Then you got routing. So it's good to know where something is, but you need Google Maps. The packets need Google Maps as well. They need to go where they're going. So routing is this. They choose best shortest path using algorithms like OSPF or RIP. These are algorithms protocols that determine which route is the best depending on specific criteria. Then you got packet forwarding, fragmentations, all that. So key protocols here is just quick one. Just don't worry too much about it. It's just so you know the names: IP, ICMP, ARP, OSPF, RIP, BGP. And you got the devices that are in the network layer, so the things that we talked about before, routers, layer 3 switches, which is a switch like that, firewalls, all that. So an analogy I like, because you can see a postcard here, because I really like the analogy of the postcard. But so think about it as a postal system. So the IP address is the street address. The router is the postal hub, which chooses the best route. You know how they deliver your packages on time? They always know the best route. I don't know how they do it, but they're really good. And the packets are the letters. All good? Perfect. So now we got this. Hold on, looks like a lot of numbers. Don't worry, it's not too much. So IP address, what's an IP address? You got a few things. You got an IPv4 and IPv6. Why does IPv6 exist? Because we realized that IPv4 addresses are not going to be enough, that we have much more devices than we thought we would have on the connected. And so we need something which has much more availability to have addresses. So IPv4 looks like that, 192.168.1.1 or something like that. So it has 250, 256, 256, 256, 256, which are, so you get that, that's the number of addresses you can associate. You know, IPv6, which is in hexadecimal, and I'm not going to go too much in detail about the formats. But yes, that's it. So what is a subnet? A subnet is, so imagine you have your router at home, you have an IP address, you have a lot of IP address that your router tells you can have at home, but do you really need those 256 times 256 times 256 times 256? or I don't know, maybe 254 addresses in total might be just enough for all your devices. I don't know, I don't have 200 computers at hand at home. I mean, I like technology, but not that much. So that's why subnets come here. So subnets help you divide the network part and the host part. So for example, here we have a subnet /24. So this is what we call This is what we call a subnet. So it tells you that all the addresses before, so to the three first here, boom, 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 255, 255, 255, are reserved for the network, and the host part, so the address you can attribute in that network, is from the 0. So /24 means you have 256 addresses minus 2 because you got addresses that are reserved for the network, which is .0 and .256, which so leaves you with 254 addresses usable. This is the hard part. Everyone is following? Questions? No? Okay, let's see. So you got a small table here to help you understand. Sorry, I didn't leave the things. So this is the first column is the subnet number. So if you have /24, which is exactly what we have here, this is the last column. So we got 255, 255, 255, and the last 0 is the last part is the number of addresses that you can assign to your network. So this gives you 254 addresses usable. And that's mostly what you need to remember from this graph. It's so okay. So what I've heard about MAC addresses, we talked a bit about IP addresses, but what's the difference between an IP address and a MAC address? So MAC address is something that is at the layer 2. Let's remember, layer 2 is data link layer, so it's the one below network layer. So why would you need something below network layer if here in the network layer is everything regarded to addressing? So you will need the MAC address because it's a physical identifier. It's burned into your hardware. So it's not something you can spoof it, but it's not something you can really change. And it's something that's unique per device. IP addresses can change, but the MAC address will not change. So the first parts of the MAC address usually in cybersecurity are used to determine what the vendor of the device is used. So it's quite useful when you try to scan and see what devices are on your network, or if you lost the device, you need to find the IP or something like that. And it works with a local network, so that's it. An IP address, as we said before, is a logical address. It can change depending on who is where in your network. There's IPv4, IPv6, and it identifies a device on a network and is used for communication across networks. So the big thing here is the MAC address is unique. The IP is unique within the network, but you might have someone in a specific part of the world, someone in another part of the world. You might have the same IP address, but you're not part of the same network. So they don't care. But within the network, you need uniqueness, and IP is unique within the network. But outside, it's not unique. MAC address, always unique. Now, let's see how a packet goes. So it's not that complicated. It's your typical home network. It looks like that. So, I mean, you don't have 2 switches at your home network, but in your organization network, so imagine your host A. You want to send a letter to your grandma, which is in the living room on host C. So you send something, you send an email, for example. Your email would go through the switch. So the switch that you all saw is something that enables you to connect different devices together. So you got your host A, sends an email, the emails go through the switch, goes through the router, and the router says, okay, they are in the other part of the network, boom, goes back through the switch, and goes back to the host. If there were no switches, it would work as well. Okay? It's just a small analogies to see if you guys understand. As you can see, the IP addresses are here, and you all have /24, which is the subnet. Okay, perfect. So, the transport layer. We saw network layer, now we need to see the transport layer. It ensures applications can reliably talk to each other across networks. So before we saw how they find each other, now we need to make sure they can talk with each other. So that's how data gets delivered, and the layer is where it goes. This is a quite interesting analogy that I would recommend you remind of, because this is the best way to really remember what's the difference between layer 4 and layer 3, which are, for me, the most important parts of the OSI model. So the functions of the OSI model and the transport layer, are segmentation, reliability, and error detection. protocols that we will see. The main ones, TCP, UDP, they're one that does all the traffic today, that gives you all the data that you need to do, streaming services, emails, websites, everything, TCP, UDP. Perfect. SSL, TLS are secure protocols that we will see, might see a bit later during the year. And the analogy I want to use here is imagine sending a large book by the post. Still the post office. I like the post office. The transport layer splits it into chapters. That's where segmentation comes in. So you want to send a big book. The post says, okay, I'm going to charge you £50 because this is heavy. You say, no way, I'm sending it in different letters. So this is the segmentation. Each chapter is numbered and confirmed on delivery. This is the reliability part. You'll see that some protocols have more reliability than others, which is useful and as well can be a bit of an issue. And last one is, if one is missing, it's resent. So error detection. All good? Perfect. So TCP versus UDP, the two big protocols that you really need to know to understand how everything works nowadays. So TCP, Transmission Control Protocol. UDP, User Datagram Protocol. TCP connects you. You need a session, so you need a client and you need a server. You need them to have secured a connection before anything is sent. So that makes them reliable. UDP, connectionless. So the guy just sends sends shurikens. One might land, one might not land, but that's UDP. They just sends a lot of data, not in order, and it's not very reliable, but it's very, very fast. So that's why we keep it today. Then TCP is a bit slower, but it's way more secure, way more reliable. So they both have something that the other doesn't, so that's why we keep them today. Example that use TCP, web uses TCP, emails use TCP, file transfers use TCP, because all this, you need to make sure that at the end of the day, you have all the data that is needed. And UDP, example is streaming, YouTube, gaming, anything like that, because you might miss some data in streaming, but if you miss for 1 second or something, it's not a major deal. But if a web page, you try to load your web page and you get half the web page, it's a big issue. So it all depends on what your applications are for TCP and UDP. I like the exercises. So I'll give you guys 5 minutes, and I need you guys to let me know, out of all these, which use TCP, which use UDP. You can work in groups, you can do anything you want. We give you guys 5 minutes. But it's alright, it's alright. Yeah. But it's a big overview, so No, don't worry.
No, it's too quick. It's too Yeah, no, I know. It's like when you're looking through something like when you're facing looking past it, you get two different things. Yeah. Wait.
Most points
This is essentially a temperature reassessment because it's getting and then obviously has a length, so it's checking length versus the packet. And if it has a full packet, then what was that for? But it's an eye. Although this Minecraft service like if you connect to Minecraft I guess I don't know. It just depends. It depends. I guess it depends on how much well,
Okay, everyone, let's get back to it. So hopefully you got everything. I'm sure everybody has all the good stuff. So I want to last analogy I would like to add that I forgot to add was TCP is like a phone call. So you call, you get the receiver that tells you hello, you say hello, then you know you got a connection, it's trusted. UDP is like you open your window, you shout in the street, and hopefully your neighbor hears you, but you don't know. That's really an analogy that can work for TCP and UDP. So let's check it out. The first one, which was watching Netflix. Who thinks it's TCP? Raise your hands. Who thinks it's UDP? And it's UDP. Well done. Speed is more important than reliability in streaming. So a few packets that you lose doesn't really matter. You might be in 180p, then you might go down to 720p while a few packets are missing. But it won't matter. It will not affect you. But it's really the freshness and the traffic is fast. That's really what's important in streaming. Next one, sending an email. If you send an email, who thinks it's UDP? Who thinks it's TCP? Marvelous. So an email, it will be TCP. So as we said before, it needs to be reliable. You don't want half of your message being cropped out of what you send. So really, TCP is absolutely a requirement for emails. Online gaming, real-time multiplayer. Does depend on the game. Very, very, very well said. But imagine for a multiplayer like Call of Duty, so something that's very fast-paced, or something that you might use for Fortnite, for example, something that's fast-paced where you use a FPS, or something that goes quick where you need real-time data. Who thinks it's UDP? Who thinks it's TCP?
It depends on the game.
Depends, but yeah,
like Minecraft, for example, in real time, like on servers, they're all done by TCP, and that's really real time.
Yeah, true. But for really fast-paced games, you do need some UDP, but TCP is also something you can use for specific games. I mean, they both use this stuff. But for the example with Call of Duty, I would say you need UDP because you need real-time data. If you have small packets that are lost, small things that are lost, there are algorithms today that do prediction on your movements, and so they try to correct this bit of data loss that you have. So online gaming, UDP, I would say, but the TCP also works. Browsing websites, as we said before, when you access a web page, you don't want to cut in half. TCP, UDP. Who says TCP? Who says UDP? You didn't say anything, I saw you. So this one would be TCP, because you don't need half of your web page, or you need reliability, you should load fully and correctly. Okay, let's not go too much into this. Web calls or Zoom, Teams, who says UDP? Okay, who says TCP? Okay, for this one, it would be UDP as well, because like the streaming, you would need low latency, so as fast as possible. If some guy says, I need you a meeting on Tuesday, and you receive it for 20 minutes later, and you're in the call with him, it wouldn't be nice. So UDP, you need something fast. Some packet loss is tolerable. Sometimes you might have freezes, things like that, thanks to UDP, but at least it's fast. Last one, downloading a file. Of FTP is a protocol that you use to download files. So what would you do for downloading a files? Would you need reliability, or would you need something fast? TCP. UDP. It was TCP. Well done. So you need a file to arrive intact. If it's corrupted, you're not very happy. If you wanted a file about your the spendings and you get half of your spendings, you're not happy about it. So this was TCP vs UDP. I think you all mostly understand what's the difference between these two protocols. These are very crucial protocols that we use for data transfers. So please keep them in mind. Okay, we see all that. But now we're in cybersecurity. We're not in computer science. So we need to understand why we look at the network parts, and what are the very big common threads that you might have that are related to networks. So we talked a bit about it at the start. Denial of service. So DOS stands for denial of service. DDoS stands for distributed denial of service. One will be a single machine sending a lot of data. A distributed would be a lot of machines sending a lot of data. So a distributed is way more of a problem, but most of the time attackers don't have a big network of devices. Overwhelm the system with traffic, a lot of data, try to kill the web page, that's it. Man in the middle. So as you can probably guess, if you have someone here, and you're in the middle, you can hear what's going through. So that's the big issue with man in the middle. Some guy may position itself in the middle of your traffic and listen to what is said between you and your host. And that's the man in the middle attack. Spoofing. Spoofing is a nice way to say impersonation. So you can fake your IP, you can fake your MAC address. Even if I said it's unique, you can still fake it, but it stays unique on your machine. And so this is used to impersonate device. So spoofing is also used when you try to call someone. I might take your mom's number and call you, say, I need you to come back to your home, and while you're not here, rob your house. Not nice. So this is spoofing. It's a very dangerous thing. Sniffing, it's capturing unencrypted traffic. So HTTP, HTTPS, that we're going to see next week. S stands for something. It's not just randomly, sometimes S, sometimes not S. N stands for secure. So if the network, the traffic is not secure, I might try to listen to what you send, and you might send passwords, you might send usernames that I might find very useful to access to your accounts. So sniffing, something that is also an attack that you can do on the network. Phishing over networks. So of course, if you don't have connected devices, you don't have phishing. So malicious emails, fake websites, all the phishing things you probably have heard about. This is also a big network threat. Someone might position itself into your organization network and might be able to access. Let there be light. Okay, nice. So someone might do some. Okay, I don't know what's happening, but no worries. Phishing. You probably all heard of it, okay? So yeah, you send some malicious emails, you send some malicious things. Hello, I'm your boss. I need some money. I'm stuck in Uganda. Please send me 20 million euros. Phishing email, not very useful, but a long time ago they used to do it, but with diamonds, not with money. But yeah, you get the point. Malware propagation. So a worm is something that replicates itself on the host or on the network, and it's something that's very dangerous, and it can spread automatically. I don't know if you guys remember, last week we talked about something called the first virus of the internet. We very briefly saw about the historical events. The first actual virus on the internet was a worm, and was something that auto-replicated itself. And you can imagine there being no virus, something that auto-replicates itself, got everyone absolutely panicked. So a worm is something that can be quite dangerous if not controlled, and it can spread very, very, very fast. And it can, so ransomware as well, so it spreads across local area networks or even one, but most of the time local area networks. And DNS attack. DNS is domain name service. So I told you guys, this is also something we'll see next week. When you type Google, how do you know where is Google? Where is Google actually? How do you know the IP address of Google? So DNS is the thing that resolves the name to an IP, and you can attack that by saying Google, or for example, something else is not on this IP anymore. It's on another IP that might be controlled by me. And so at the end of the day, I send you on something that I control, and I can send you click some malicious links, things like that. So DNS attacks, very dangerous as well, but you need a lot of control to be able to do that. Poisoning, hijacking DNS to redirect traffic. So we saw now firewalls. Firewalls, probably all heard about firewalls. Definition that I have from Cisco this time, because I didn't find a good one from IBM, is a firewall is a network security device that separates a trusted internal network from an untrusted external network. So it's really a wall, a big wall, and you put your rules that you want in place to say, okay, if traffic comes like this, I don't want this in my network. If traffic is like this is okay, it can come through. So it's really border control, saying yes, no, that's it. Key functions: regulates incoming and outgoing traffic, enforces preset security rules, blocks unauthorized access, and allows a legitimate connection. If you identify correctly. If you misconfigure your firewall, you will see very, very fast that you don't get any traffic, and you might spend a lot of time trying to understand why you don't get any traffic. So that's it. There are multiple types of firewall. We are not going to go through the list. It's not exhaustive. Packet filtering, stateful, proxy, firewall. I mean, all the big names and complicated names. But at the end of the day, it mostly does the same thing. You put in rules, it monitors your traffic, and it checks if your rules match some stuff or don't match some stuff, and lets it through or says, no, go back from where you came. So that's firewalls. What's a VPN? You might have used VPN. You might have a lot of publicity about NordVPN nowadays. So, you might have seen stuff about Proton VPN, NordVPN, all the ones. I don't have all the names in head, but VPNs stands for Virtual Private Network. Describes the opportunity to establish a protected network connection when using public networks. VPN encrypts your internet traffic and disguises your online identity. So VPNs make you use another IP than the one you might use originally to access the internet. And it also encrypts your data or your internet traffic, which is quite useful when you're connected to a public network, because you never know who has the public network. Privacy. So why would you use a VPN? Privacy, security, because hides your IP, encrypts traffic, like I said. Remote access, connects securely to a company network. This is very used in the professional world. They might ask you to install a VPN to connect to their services, or if you don't have the VPN, you won't be able to access any of the services. And of course, if a company, like we said before, is a WAN, so has a lot of places, a VPN essentially gives you access to the internal services, which is perfect. And you can bypass certain restrictions, because we know content is blocked in certain areas. So VPNs is really, really nice to say, I want to be in Canada right now, and you can access stuff that is in Canada. So this is quite nice. Common protocols. You might think that VPN is a protocol in itself, but it's not. So big VPNs use, most of the time, one of these three protocols. OpenVPN, the oldest one and the most common one, IPsec, also very common. WireGuard, more recent, but very useful as well. So these are three protocols that are used by VPNs. And you might try to ask why I put this meme right there, because I really like it. So if you use a VPN, you might have seen you get a lot of CAPTCHAs, like you get a lot of CAPTCHAs. And this is actually due to the fact that so VPN gives you an IP, and this IP might be used by other people as well. And this IP might be used to do stuff that is not legitimate. People might use this to send a lot of data to some websites, or stuff that you wouldn't like to do with a VPN. And so most of the time, you get these CAPTCHAs because some websites say, okay, I see you send 20,000 requests from this IP to a specific website, and I want to make sure you're not a bot. Boom, you get a CAPTCHA. But you got specific VPNs that have an option to try to disable it and give you specific IP addresses. So, last thing we're going to see for today is how to use specific tools. So I know at the start I said that I would go on the tools part in term 2. but I changed my mind, and I think when I talk about subjects, it's good that at the end I give you guys insight on the tools you can use on these subjects. So you feel free to let me know if you don't like it, and I change it again. But so the first tool I want to use is a very basic one. You might use it. You can use it on Windows. You can use it on Linux. You might be even able to use it on Mac. So this is pre-installed on every OS. So if you have a computer on your hand, you just like ping some pings and IP, sends an ICMP echo packet request. So it's a protocol, just says it's a packet where you say hello, are you there, and you get a response or you don't get a response, and it enables you, when it's allowed when the response is allowed, enables you to check if a device is online or not. Quite useful, because when you got something and you want to check if it's here or not on your home network, ping, IP, done. So you can add a few specific commands to your ping. So the -n one is to add the number of packets you want to, the number of requests you want to send. The T1, I don't know its size. Let me double check something. Sorry. No, sorry. The L1, my bad. Sorry, is to specify the size, so number of bytes you want to send within your packet. So of course, this can be quite useful if you want to send a specific number of bytes, things like that. And the I is time to live. Time to live is the life your packet is going to have when you send it. So it's good, if you put a time to live to 1, your packet is going to do 1 hop, then it's dead. And it might be 3 hops away, the device you want to see, but you're not going to be able to see it to know because your time to live is too short. So it's always good to have a big time to live. You also ping Google, which is quite nice. Not only an IP address, so you can ping a domain. So as I said before, then something called a DNS, which resolves domains to IPs. So here you can see I ping Google, and I see on my responses reply from 216, say 58. So my DNS resolved Google to this IP. Wonderful. So you can not only ping IPs, you can ping domains as well. And so last exercise before I let you guys go is, I showed you guys the options before. With the screenshot you can see here, what does this command do? So you can see I added 3 options. N, I, L, and the IP address. What does that do? Yep, go for it.
It pings the IP address, it's local network.
Mm-hmm.
That sends 2 packets. Each packet is 64 bytes, and each one bounces 12 times.
Almost. Each packet has a time to live of 64 and bounces 12 times. It's a hard one. I don't know why they chose I and L because it makes no sense. But so I shortened the original time to live, and I said I wanted lower sized packets because I know where the device is in my network, so I don't need to go for it a very long time. So that's exactly what we said. So it sends 2 ICMP echo requests with the -n, time to live, okay? So you get the idea. I'm not going to go in details on that. But one last thing, you might think, we talked about denial of service before. We talked about sending a lot of traffic to something and making it drop. Could I not use this to send a lot of packets and drop my service? Long time ago, it was possible. Nowadays, you got a lot of devices that don't respond to ping requests because they know this is possible. So you got ping floods, which is the name of the attack, where you send a lot of pings, and you try to down with only ICMP echo requests. It's not a big, very resource expensive thing to do, so it doesn't work nowadays if you don't have a very old school device. But it's still nice to know that we were able to do it a long time ago. So last tool I wanted to show, but I thought we wouldn't have time, is Wireshark. This is going to be the theme of the workshop that we have this Thursday. So yeah, I'll let you guys show up on Thursday if you're interested in that. And next week what we'll see is web basics. So what's the web? Why does it exist? Web protocols and how they work. So we saw a few of them today. HTTPS, HTTPS. Can a domain name resolve to an IP address? Probably guess so it can. And common web vulnerabilities, which is web is a big vectors of vulnerability in cybersecurity. So that's the interesting part. The sources. And that's it for today. Thank you guys for attending. If you have any questions, feel free. I'm not moving from the desk, so go for it. Thank you guys.